Hello. In this lecture, we're going to discuss species conservation. In the previous lecture, we concentrated on the conservation of the total density in the medium. So in this one, we will be specific and we will assume that we have a number of species and the species is designated with an index I and it's moving with its own velocity, v sub I. And then we have an average velocity for all of these species in a mix. Suppose that we're studying chemical vapor deposition, then the mix will be in a gaseous phase. If we're studying, for example, solidification, we have a liquid, then the mix will be moving in a continuous casting process, will be moving in a stream, and it will have some kind of an average velocity. So we will establish the conservation equation on an integral sense, reduce it to a differential form, and then see the approximation if we have an incompressible fluid. So let's try to do these steps here. So in the beginning, what we will do is we will look at the species conservation as the sum of all of the rate of change of the concentration of species I, which is denoted by rho sub I, plus whatever is crossing the boundary. So the boundary we designated by partial omega. So what is crossing is the flux of species I. We're going to denote it as v sub I with a bar because it's the vector, and is crossing the boundary, and the boundary has a normal unit vector n, and the element of area is ds. So as we know, we have now a boundary, and we have rho sub I inside, and then we also have j sub I that is crossing a mass flux that is crossing. So the rate of change of rho by dt and the mass flux, if we just account for the areas and the volumes, that total rate of change should be equal to whatever is produced inside that volume. And whatever is produced inside the volume is expressed as a volume integral, with the production rate is r sub I, dot is because it's a rate, this is a time rate, triple prime because it's per unit volume, d omega. So this is the chemical rate of production of species I. So, and as we mentioned before, the whole idea is that you get an integral equation. So what you do is you take the surface term on the boundary, and then you use Gauss's theorem to cast it into a volume term. And then the next step is to assert that the equation has to be satisfied on a local level because that's the only guarantee that we would have the sum of all of the terms equal to 0 under the integral. And that gives us what's called the strong form of the conservation equation. So the weak form is the integral form. The strong form is the differential form. So let's do these two steps, the Gauss and then the localization to the strong form. So if we do the Gauss, then we would have and pull out the d by dt outside the integral, and then we have volume integral of rho I d omega, plus now the Gauss gives us the divergence of rho I times the vector v sub I d omega, and this is equal to the volume integral also of r sub I dot triple prime d omega. Notice that now I have everything in these equations as integral over the volume, and therefore I can localize it by asserting that the terms under the volume integral, all of them have to add up to 0, which means that I get the strong form is d rho I by dt plus the divergence of the product of rho I vi equals to r sub I dot triple prime. So now we got now the strong form of the equation. So if you can see, you will see that this is a strong form, and then it is in terms of the velocity v sub I. So what I need to do is find the relative velocity, which is the difference between v sub I and the average velocity, and introduce that into the equation, because if you have a stream that is moving, some of the particles will be moving back and forth in their own way, but everything will be carried with an average velocity that we need to account for. So the fluxes will be relative in the sense that they're moving with the stream. So let's introduce this average velocity here, and then we use it in the equation. So if we say let v bar with these brackets to be the average velocity, that is for the whole stream, and we can actually use this to define a relative velocity. So if you have a relative velocity v bar I relative, it will be essentially vi minus this average velocity for the entire system. So in this case, what we will do is we will rewrite the equation. We will add and subtract the average velocity. So I have d rho I by dt, and then I will have the divergence, and the divergence now is going to be rho sub I times the average velocity. We added that, so we must subtract it again here, and then we have the original term, which is rho sub I v sub I here, bar, and that is equal to r sub I dot triple prime. So now the equation is defined in such a way that I can write it d rho I by dt plus the divergence is going to work on the first term. So it's going to give me rho sub I times the average velocity here, plus the divergence of the rho sub I times the difference between vi and its average value. So that's going to be all equal to r sub I dot triple prime. So now we have identified that if you look at this term here, this is the drift flux of element I in the mix. So it's kind of a relative flux. So we're going to call it J sub I and give it a vector here. That's a relative flux. And we also know that we have this term here is the what we studied before. We can write it in a different way. So let's just continue on for the next page here, and we write the equation in slightly different form. So if we write this equation here, then I will have d rho I by dt plus the divergence of rho I times v. So we will have maybe rho I here times v average, and then this will be equal to, I'm going to take the divergence of j I on the other side plus r sub I dot triple prime. And now what I would like to do is just show you that this term here is equal to 0 if we have an incompressible fluid, and then we'll pull out one term out of it. So we're going to write it like this. The divergence of rho I v average is equal to the first times the derivative of the second, which is the divergence of v average, like that, plus the second, which is v average, times the gradient of the first. So we have v average, and the v average is dotted with the gradient of rho sub I. So we have also shown that if we have an incompressible fluid, then the divergence of the velocity, average velocity, is 0. Therefore, now this term here becomes only the v dot grad rho I. So I have d rho I by dt. If I go back to this equation, I have d rho I by dt, and then substitute now v average dot divergence gradient of rho I equals 2 minus the divergence of ji plus the production rate from the chemical reactions. We also know now that we could write this in an operator form, like d by dt plus v dot grad as an operator operating on rho I, and this will be equal to minus the divergence of ji plus r sub I dot triple prime. So that's here what we have in the whole system. So in the whole system now, if you look at it, we have now a situation where we have an equation that tells us that the rate of change with respect to time of the density for rho I plus the dot product of the velocity, average velocity, times the gradient of the density of rho I, that sum is equal to, on the other side, minus the divergence of the flux of element I plus the production rate. So what is remaining here is to concentrate on the left side. The left side is going to be shown to be the material derivative as we've seen it in the previous lecture, and we want to go one step further to convert the density rho I into a fractional density. We're going to call it m sub I. So these are the remaining steps in producing this equation. So if we look here at this equation here, let me just add another page, and we have here in this equation, if we want to produce it, it will be now, instead of having these two on the side, we're going to write it as like the material derivative of rho I plus, we showed that the material derivative is basically the sum of the two derivatives before. Then this will be equal to minus the divergence of ji plus r sub I dot triple prime. And we're going to let now m sub I to be the fractional concentration, which is rho sub I divided by rho, and introduce it here. So rho sub I will be equal to rho times mi and everywhere else. So we will have this rho sub I will be equal to m sub I times rho. And then when we do the derivative, then we take now d by dt of rho sub I will be equal to d by dt of m sub I times rho. And again, using the chain rule, this is the first times the derivative of the second plus the second times the derivative of the first. Let me just write it clearly here, times the derivative of the first, mi by dt. So that's now the total derivative, and we know now from mass conservation, total mass conservation of the previous lecture, that this term is equal to 0, and therefore if you look at the left hand side, which is this term here, now it becomes only this term, which is rho times d mi by dt. So now we can cast the equation in a more useful form as d by dt of mi is equal to the divergence of j. And the j sub I, what we'll do is we will have to use Fick's law to write j sub I for that stream. So that will be our next step. If we just add another text box here, maybe we add another page to this here, then we can write the equation as Fick's law tells us that j is equal to minus rho d sub I times the gradient of m sub I. So this is Fick's law. And di is the diffusion coefficient in the mix of species I. And therefore, the conservation equation for species I will be capital D mi by dt will be equal to the divergence of rho di grad mi and plus r sub I dot triple prime. So we have now a nice form that we could use for a moving fluid, for example, like in casting, if we are looking for the concentration of different species. And in this equation, we have the total rate of change, the material derivative of the fractional concentration of species I. The rate of that is equal to the divergence of a flux plus the rate of production, chemical production, if any. If we don't have any, then there will be zero. The divergence of that flux, the flux is written in terms of Fick's law because it's a diffusive flux in this case, because species I is moving with the system, so it is relative to the average motion of the whole system, and therefore it has an effective diffusion coefficient d sub I. So that's basically what we need to solve for the species conservation in our system. In many applications, we have, for example, either stationary or very low speed flows, and we can make an approximation to get a more familiar form that we use in diffusion processes during the material thermochemical processes of materials as follows. So the next step here is to have another form that we can, the approximation that we have is now we're going to say that if we have low speed flow and constant diffusion coefficient, and the rho is also constant, and we have constant Ri dot triple prime is equal to 0, then we will get this special case, and the special case is partial mi with respect to t is equal to a diffusion coefficient times the Laplacian of mi. And what happened is that I pulled out, so let me highlight this, is our now time-dependent diffusion equation. So this is time-dependent diffusion equation. And the solution of this time-dependent diffusion equation will determine the concentration of species I. Notice that I assume that di is constant, so I pulled it out of the derivative, and rho also is constant, I pulled it out of the derivative. And in this, we have now finalized our derivation of the equation of species conservation for any element within a mix, even if it is moving, or the only caveat that we have is that we would have an incompressible fluid that we will have to model in our system. So we're going to stop here, and then we'll continue our derivations for the conservation equations in the next lecture.